we're going to take a look at the application of kinetic versus thermodynamic control and the reaction of conjugated dienes with HBr, or any HX for that matter. So what we've already learned is that we should number our diene. And again, in this case, we're dealing with a symmetric diene, so it actually doesn't matter which direction we number from, we'll get the same products. In the next example, we'll look at an asymmetric diene and see how to deal with it. So the products that you would expect for this, if you were to go through the mechanism, we would expect the potential for a 1,2 product. And we add the Br here, and if you want to draw it in, the hydrogen here. And then we would expect a 1,4 product, where the double bond is now in the middle. We add a hydrogen here, and a Br here. Again, if you want to stick with numbering, one, 2, 1, 4. But depending on our conditions, we can affect the product distribution. So if we were to carry this reaction out at a low temperature, a common low temperature would be minus 78 degrees. In this case, the 1,2 product is going to be the major product, and the 1,4 product would be a minor product. On the other hand, if we were to carry this out at high temperature, let's even say 40 degrees, or it could be higher, this is going to switch things around, and in this case, the 1,4 product here ends up as the major product. The 1,2 product that is formed at a lower temperature, that's known as the kinetic product. And when thinking about kinetics, that's all about speed. And the kinetic product is formed faster. Versus thermodynamic, which is what we have with the 1,4 product here. Thermodynamic products are those that are overall the most stable. And that's what we often find with kinetics and thermodynamics. A reaction under kinetic control will give you the one that is formed the fastest. A reaction that's under thermodynamic control will give you the overall most stable product. Let's look at an energy diagram for this process, and then we'll talk about why we get these particular products. So here's what's happening in the progress of this reaction. We start with our starting material. I'll put it right here. And it goes over some transition state and drops down at the carbocation intermediate. We'll put that right here. And then from that carbocation, we'll end up with the 1,2 and the 1,4 products. So let's draw them out. And we would expect the products to show up here on the right. And I'm going to do them in different colors. So the 1,2 product is a little bit less stable. So I'm going to draw it a little higher. The 1,4 product is a more stable product. I'm going to draw it a little bit lower. Why is the 1,4 product here more stable? It's all about double bond substitution. If you look at both of these products and look at the double bond substitution, with this first product, you have 2 hydrogen and 2 carbons attached to the double bond. This is a di-substituted double bond. Versus in this second product, if you look at the double bond, there's 4 carbons attached. That's tetrasubstituted. More double bond substitution is more stable. So we'll even write that here. More alkene substitution is why that product's favored. So now we want to go over a transition state to get to each of these products. The 1,2 is formed faster. That means the transition state is easier to traverse, so it's going to be lower. So let's just draw it right here. The 1,4 product is going to be a bit harder to traverse, so we would expect its transition state to be a bit higher. But eventually, we'll overcome that and get to the product. The lower energy transition state for the 1,2 product is due to that proximity effect. Whereas in the case of the 1,4 product, you don't have that proximity effect, so it's a little bit harder to traverse the transition state, but in the end you get the overall more stable product because of the more substituted double bond. In the case of the low temperature, what we have is the low temperature will allow this 1,2 product to form faster, but the low temperature prevents the reverse reaction. So what that means is you form the 1,2 product and you stay there. Okay, in the case of a higher temperature, you're certainly going to get 1,2 product forming because it's formed faster. So at a higher temperature, yes, we're going to get 1,2 product, but at that higher temperature, this reaction will be reversible, so we'll go back, and then this might go over the other transition state to get to the 1,4. And this equilibrium will happen until everything gets converted to the overall more stable thing, the 1,4 product. So because the reaction is reversible at the higher temperature, equilibrium drives the reaction to the more stable product overall.